Hi everyone, and welcome to this free introductory course on Kubernetes. Something I see often when people try to get started with Kubernetes is that they'll be overloaded with theory and terminology of how Kubernetes works, but without actually seeing these components in action. You can end up with this conceptual idea of Kubernetes, but no real experience of Kubernetes. Personally, I like to have a lot more hands-on experience to learn, as this gives a deeper understanding of the components and overall helps with the learning experience. So, this course is different to others and it follows the path of how I personally manage to fully understand the individual components that make up Kubernetes. We're going to start with the setup of a container runtime that we'll actually use to run our containers. We're then going to install Kubernetes and we'll launch some common components. So we'll launch pods, deployment, services, etc. If you're new to Kubernetes, don't worry. We'll actually cover these various items as we go through. Then, and this is where this is different to other courses, we're going to tear all of this down, and I don't actually mean nuking this here. We're going to actually take these components down systematically, but in a way where we can easily put them back for learning purposes. As we do this, we'll talk through the individual components methodically, and we'll explore stage by stage with focused examples what each piece of Kubernetes architecture actually does and why it's actually important to Kubernetes. So, let's dive into Kubernetes. I've provisioned a simple AWS host and I've chosen a generic Ubuntu build with 2 cores and 8 GB of RAM, which will be very easy for you to replicate, whether this is actually on your local system or via another cloud provider. If you wish to follow along, as well as subscribing to my channel and following me on Twitter for more awesome content like this, I'll also include in the details references to the commands that are actually being executed. So the first component that we're actually going to look at is our container platform. Now, historically, the go-to choice for many on this would have been Docker. And personally, I absolutely love Docker and I use it extensively in my day-to-day. And I encourage you to do the same if you're not actually doing this already. Many people reach out to me and they ask how to actually learn Kubernetes. And I typically ask, have you learned Docker? Surprisingly, many just try to go straight to Kubernetes. Docker is a super convenient platform, but the term Docker actually applies to many different things. So you've got the Docker container runtime, you've got Docker images, Docker Hub, and Docker Desktop, which is a super convenient desktop offering. There's a whole ecosystem around Docker. If you haven't learned Docker, at the end of this course, circle back and take a good look. For now, continue and we'll cover off any areas that we actually need as we go through this. So, where does Kubernetes fit in this? Kubernetes is a container orchestrator, i.e. running containers en masse with all of the built-in scaffolding and scalability that your applications need to run as you desire. We're not going to be installing Docker here as part of our Kubernetes setup, i.e. our container runtime. Instead, we're going to be installing what is known as Containerd. To elaborate, Docker was open sourced back in 2013 as a tool set with everything needed to actually build and run containers, and this was clearly a monumental milestone in computing. It largely shaped the way in which we use Linux and DevOps in general. Over time, more and more tools evolved around the Docker ecosystem, one of which being Kubernetes for container orchestration. Kubernetes made use of a component known as Docker Shim to interact as a layer that actually sits between Kubernetes and Docker, therefore allowing Kubernetes to use Docker as the container runtime. Docker spun off their container runtime into projects called Containerd and runC. These were respectively donated to the CNCF, the Cloud Native Compute Foundation, and the Open Container Initiative. So now, rather than actually Kubernetes using Docker Shim to communicate with Docker, which has far more functionality than Kubernetes actually needs, Docker Shim, the bit in the middle, has been deprecated as of Kubernetes 1.24. This is not a problem though. Instead, we can use Kubernetes with Containerd, which internally uses runC, which are essentially the internals of Docker anyhow. So if you're using Docker Desktop, you'll be using these components, and you may or may not even know that. So, without further ado, let's start by installing Containerd. We go to our terminal, and let's switch to the root user. So I'm going to do a sudo bash there. I'm going to change to the /tmp directory, and we'll run an apt update just to populate apt. After that, we can install Containerd again using apt. You can see there that it's also installing runC, the container runtime that I just spoke about. After that's done, we can then control Containerd using systemctl. So we'll enable it so that it actually starts on reboot, and we'll start that up, and we can just do a status there. Okay, so with Containerd installed, Containerd is provided with an unsupported tool called CTR that allows us to actually interact with containers. It's unsupported and is a debug administrative tool, and that's actually the terminology used by CTR itself. If you've used Docker before, you'll see a huge difference in the ease of use, as Docker has really spoiled us, and it's extremely slick with its command line interface. The great thing is, there's a project called nerdctl that actually provides a lot of the Docker CLI experience that we love for Containerd. Let's take a look at this. The project's called nerdctl and is a Docker-compatible command line interface for Containerd. Whilst we're here, notice that it mentions that we also need to install CNI, Container Network Interface Plugins. Firstly, we'll focus on Containerd, and then we'll come back to those plugins. Okay, so we're going to grab that from the releases section. So copy that hyperlink, and then we're going to pull this down. So wget and paste that. Okay, so now that we have this, we just untar that. And we're going to move nerdctl to /user/local/bin. Okay, so with that done, let's now grab the plugins that it mentions. So from this page, we go back in our browser, scroll down to the Cni Plugins there, and click the link. This is the Cni Plugins page. Just go back up there to Releases, click Releases, and scroll down to the Assets. And here you just need to right-click and copy the link for your architecture. Okay, so again, we download this with wget, and we're going to create the target directory, so opt cni bin, and we're going to untar this tar file specifically to opt cni bin, which is why I'm using the -C option there. Okay, and with that done, if we like, we can actually try to run a Docker-like command, but quite simply substituting the word Docker for nerdctl. Okay, so we're telling it to run --rm to clean up, -it for interactive, Ubuntu is the image, and bash is the command. So we can see that that's downloading the image, and we're running in the container. So you can see this there as the host name has changed. We can take a look at what processes are running. So in this case, it was just running it with bash, and you can actually see that there in the PS output. And we could run other commands. So I'll just do a uname -a here, and that's good to go. So let's just exit out of that container for now. Okay, nice. So we can see that as a user, we can interact with nerdctl, giving us the Docker-like experience for containerd, which in turn uses runc, which in turn runs our containers. So far, this looks like the following. We can see the Cni plugins that we installed for nerdctl, and going forward, I'll be referring to containerd and runc as the container runtime components. Okay, so time now for us to up our game and install Kubernetes. For this, we're going to use kubeadm, and the reason I choose this, kubeadm gives a very clean cluster. So some micro Kubernetes distributions, they run components or subcomponents in containers or with modifications to minimize overhead. This can make it a little bit more difficult to really see and understand how the architecture, or in particular, the Kubernetes distribution in question, hangs together. Also, kubeadm is fantastic. If you're studying or planning to study for the likes of the CKA or the CKAD, typically a lot of questions focus on kubeadm built clusters. So this will actually help you out if you're planning to take those exams at any point in the future. So let's go to the kubeadm page. We're going to scroll down past this first section, and quite simply, we're going to copy and paste these blocks. Now, watch out for this, as it catches me out so many times, and it's really important that you run this command, which it actually mentions just there above. Scroll down further, and then we'll copy and paste each of the following. When we install Kubernetes, I'm going to supply the pod network CIDR. This is the range of IP addresses that the pods, the smallest unit of compute in Kubernetes, i.e. a group of one or more containers, will use. I'm going to give this 10.10.0.0/16. Typically, you don't need to do this. If you've ever set up a cluster with kubeadm before, you'll know that after setting it up, you need to install a CNI, a Container Network Interface, to make the nodes become ready. When you run one of the numerous CNI options, you would typically run them against Kubernetes, and they would install components and configurations inside of Kubernetes automatically. I want this setup to be lightweight for simplicity, as this is a cluster for our learning experience, not for production. Therefore, I'm literally going to use a very simple, lightweight CNI approach rather than a more sophisticated network stack. Recall, when we installed nerdctl, we also installed the Cni plugins. We're going to use these plugins for a simple container network interface, and for this to work, we need to tell Kubernetes the pod range, hence that extra option there. So that's installing. kubeadm will detect containerd and will configure accordingly. There we go, we're done. Now, remember that path there, etc Kubernetes Manifest and the term static pods. We're going to come back to this later on. For now, let's copy and paste this line. This variable is used by kubectl to reference the required information and authorization to communicate with the API server. If we do a kubectl get nodes, we can see our single node control plane /master. For convenience here, I'm going to set a variable of k8_master with that node name, so I can easily refer to it later on. I just echo that variable, and you can see that that's actually stored there. We have one node, but at the moment it's not ready. The reason being, as I mentioned before, we don't actually have a container network interface, CNI for short. If we take a look at the Cni plugins that we installed, specifically the bridge plugin, this gives us a very simple CNI interface which will actually satisfy our single node configuration without us actually having to have networking components running inside of Kubernetes. It will keep our setup very simple for learning purposes. I'm going to create a file in etc cni net.d, and it uses a numeric system for naming, so I'm just going to use 10 and we'll add -bridge.conf. Notice the subnet there is the same as the one I passed to kubeadm in it. That's specifically why I used that one, so that I didn't have to actually edit anything later on. After this completes, I'm going to actually follow this with a watch command so we can actually see the status change in real time. Okay, perfect. This will have also automatically created the mynet0 bridge that we saw in the example, and you can see this here in the IP-addr output. By default, a cluster installed with kubeadm will not allow any workloads to be scheduled to the master node. Kubernetes uses a concept known as taints to control this. So if a component has a taint, whatever is interacting needs to have a toleration, i.e. it needs to be able to tolerate the taint. It's a bit like myself and my wife. I can be a bit annoying sometimes, which is my taint. She's able to tolerate me being annoying, hence it actually works. We're going to keep this simple. We're just going to actually remove the taint. Now, if only life was as simple as it is in Kubernetes. If we take a closer look at our node, we can actually see all of this information. And if we scroll back up there, we can see the taint section. And I'm just going to capture that taint. Adding and removing taint in Kubernetes is simple. It's literally the same command to add or remove, but with or without a minus at the end. So here it's a minus as we're removing the taint. And if we check again, you'll see that the taint is gone, allowing us to actually schedule workloads to the master node. Now, I wouldn't recommend this in production, but for learning purposes, it's okay. By the way, this is also what some of the smaller Kubernetes distributions do that also run as single nodes as well. They don't actually have that taint set. As we go through this, we're going to need somewhere to keep some resources. So I'm just creating a directory called etc Kubernetes/resources. Now, this isn't a standard directory. This is just something that I'm going to use as a store for information as we go through this. Okay, so now our setup looks like the following. We have our Kubernetes cluster built with kubeadm, which would be using CRI container runtime interface-containerd to talk to containerd. CRI-containerd also connects to the CNI, the container network interface, and in our case, it's making use of the Cni plugins. Using our kubeconfig file, we can then communicate with Kubernetes. We need to break this Kubernetes entity into smaller chunks to understand it. So let's dive into the detail. Kubernetes makes use of a lot of YAML, but a lot of the time, you don't actually need to fully create that YAML from scratch. A lot of it you can generate fully most of the way with kubectl, or you can actually pick up YAML references from the official docs, so Kubernetes Dot Io. This is really important to learn if you're doing the exams, as this gives you the speed element that you absolutely require for passing those exams. To demonstrate it, so for example, if we wanted to run a simple pod, and for those of you who are really new to Kubernetes, a pod is the smallest deployable unit of compute and is simply a group of one or more containers. It provides shared networking and storage, and you can think of a pod as an isolated host serving the needs of the application that it serves. To show this, we can just run kubectl run nginx --image equals nginx. So we're actually naming this nginx and we're telling it to use the image of nginx. If, however, we just wanted the YAML, we could add to this --dry run equals client and -o for output, and we'll specify this as YAML. If I press return here, you'll see the YAML declaration for this pod. I'm going to store this simple YAML reference for use later, so I'll just redirect this to a file in etc Kubernetes resources, and we'll call that nginx_pod.yaml. Okay, so now let's run this and see what happens. I've updated this here, so we've actually got two commands. We're going to run an nginx pod, and straight away I'm going to actually watch for changes. So we're doing a kubectl get pods -oy to give us more information on the output. And at this point, it's pulling the nginx image, and that's running. And if we capture the IP address, and you can actually see there, we've got the standard Nginx default homepage output. All of this was in the Kubernetes ecosystem, but we know that Kubernetes would have actually sent this to the container runtime, which in our case is containerd. So let's actually take a look from within containerd using our friend nerdctl, which again would be just like using the Docker CLI. We do a nerdctl ps-a. We don't actually see anything there, but it is there. It's just hidden in a containerd namespace. We do a nerdctl namespace ls. You can actually see that, and we'll specify that namespace. So nerdctl-n k8s.io, and then we'll do a ps-a. There's a lot of containers running. The focus is specifically these two. If you look carefully also at that output, there's a lot of these pause containers, and here I've actually annotated this output to show that there's a single pause container for every pod. At this point, this is a good time to actually explain the pause container, as you're going to see lots of these about, and again, a personal annoyance. Most Kubernetes architecture overviews completely skip this. To understand this further, we're going to actually use our good friend Docker, as this example works better in Docker than in nerdctl. So remember, nerdctl aims to be a Docker CLI compatible interface, but it's not fully there at the time. On my local system, I'm going to run the same pause container used by Kubernetes. Remember, it's just a container. Docker is a container runtime engine, and there's nothing stopping us running this ourselves. It's not exclusive to Kubernetes only. So we do a docker run -d to detach. We're going to set the IPC, inter-process communications, as shareable, therefore allowing the container to communicate via shared memory. I'm going to name this container pause. I'm also going to expose port 80 inside this container to 8080 on my local machine. This pause container doesn't actually have anything running or listening on port 80, but stick with me and we'll actually see why as we continue through this. So that's there, that's actually running. You can see the container ID. Next, I'm going to run a MySQL container. So here we actually do a docker run to detach. We're going to name this MySQL, and we have the standard environment variables for the MySQL container. So MySQL database, which we'll set as example DB, MySQL user as example user, MySQL password is example pass. We'll tell it to actually set a random root password, and we're going to actually use the net, IPC, and PID environment from the pause container. MySQL will actually be running in the pause network namespace, and it will be listening on the standard MySQL port of 3306 within that namespace. Then we're actually going to run WordPress in the pause network namespace. Again, similar to what we actually did with MySQL. So -d to detach. We're going to name this WordPress. Here we have the environment variables that respectively tally up with MySQL. I've just annotated there that you can actually see where these match. And again, we have the same net, IPC, and PID of the pause container, because MySQL and WordPress will then be in the same namespace. MySQL will be visible on that local network to the WordPress container. WordPress will listen on port 80 in that namespace, which of course is bound to port 8080 on my local system. So remember where we actually did the setup of the pause container earlier, we put that in place. Therefore, I can now connect to localhost 8080, which in turn will then connect to port 80 of WordPress, which is using the pause network namespace. So I'll bring up a browser and we can connect to localhost :8080, and voila, that's actually working. And just to quickly show this, we'll go through the wizard here, enter in some default values. We've got the welcoming page of WordPress. So through this pause container, we've got multiple containers sharing a network namespace. We've essentially just manually created a pod in Docker, which is similar to what Kubernetes will do and is essentially the purpose of the pause container. Going back to our Kubernetes setup, let's hide that pause container output in our nerdctl view there. To recall, we ran a pod in Kubernetes and we can see this container running inside of containerd. Now, what happens if we actually manipulate this container outside of Kubernetes directly in the container runtime? I'm going to stop this container, and following that command, we'll actually use watch to track the output from the Kubernetes side with kubectl get pods. There we go. The Nginx pod was created with restart always by default. It's been detected that it's not there, and voila, it's recreated. Hence, the restart count has increased. What happens, however, if we kill the pause container, which, as we saw, is the foundation for the networking of all containers in that pod? And watch here. Notice how the IP address changed as the pause container controls the network namespace for the pod. So we actually saw an increment of the IP address. It basically took the next available IP address from that Cni plugin. Next, we're going to run an Nginx deployment. So a deployment is a declarative means for defining a desired end state. So we can use deployments to specify how an application should run, as well as the number of replicas that should be running. Deployments also provide useful interaction points for other areas in K8, such as services, and we're going to actually see this as we go through. Let's create a simple deployment using Nginx again. This time, we'll also specify port 80 in the deployment construction. So again, here, I'm just going to use kubectl. So kubectl create deployment. We're going to name this Nginx. We use the image of Nginx and we specify the port of 80. If we get the deployment, you can actually see that this has a top-level name of Nginx. Deployments, in the way that we've actually deployed, automatically get a replica set. And you can see there, we've got an identifier appended for the replica set. So just a kubectl get replica set to see that. If we look at the pods, these are then named accordingly, as these are being provided as part of that replica set with their own unique ID at the end. So with our deployment running, if we take a look from the container runtime, we can actually see this running here. Notice the name, as this is a deployment, so we can actually try to scale this. We'll increase the number of replicas and we'll also run our watch command straight after. Okay, so you can actually see these appear, and from nerdctl, we can also see these. As we've seen before, if we were to kill the pause containers, our IP addresses will change, as we would have lost the core networking of the pod. Let's actually try this out again. And you can see there that the IP addresses changed. So to facilitate this, we need something consistent, which is where Kubernetes shines. We can create a simple service to point at the deployment, therefore giving us a fixed endpoint. We can do this from the CLI, and we'll expose the deployment with a cluster IP. So we're going to do a kubectl expose deployment /Nginx. So that's actually specifying our deployment of Nginx. And we'll do this as a type cluster IP. And if we take a look, we can actually do a kubectl get service. And now we can actually curl that IP address. And again, if we were to actually kill the pause containers, it doesn't matter, as the service will automatically update accordingly. So let's just do that. We'll do a nerdctl ps. We'll limit this specifically to Nginx and pause and those that are actually up. And let's stop both of those containers there. And straight after that, we'll do a watch so we can see this in real time. And yeah, those IP addresses have changed. But if we actually try out our curl, that's all still working as expected. So that's the beauty of services. So lastly, with Kubernetes, you get a fantastic DNS resolution service built in when you use services. So if, for example, we run another simple container with curl pre-installed, so I'm just going to actually use the curl images / curl image. And again, this is a bit like Docker run --rm to remove -i for interactive, tty. Curl is the actual name. We have the image there. Restart, we're just putting that as never. And we have -- as the command separator and sh as the command. Now we're here, we're actually inside that curl images container, and it's just super convenient for using curl. We can curl the name of the service, which is Nginx. The namespace for this that we actually run it in is the default namespace, and then we just append on svc.cluster.local. And as you can see there, this is working. DNS is actually built in there for the win. So we'll just exit from that, and let's delete and clean up what we've actually got there. Okay, so this is actually running and it's great, but there was a lot of Kubernetes infrastructure magic that went on that we don't actually know about. If we take a look at what is actually running from both a nerdctl viewpoint and in Kubernetes, and for convenience, what I've actually done here is I've annotated the containers running there in containerd to the bottom output that we actually see there in Kubernetes. We also have the Cubelet running as an independent process. Now, we're going to start removing components from Kubernetes and shutting it down accordingly. As we do this, we're going to capture information accordingly so that we can actually put it back together later on. Okay, so we're going to do a kubectl get all -a, and you can actually see the kubeproxy, which is a daemon set. This actually means that it will run on all nodes automatically. We're going to capture the YAML from this, and then we're going to actually remove it. So -o YAML to actually output that there as part of the get command. We're just redirecting this to a file, and then we're actually going to delete this. And next up, core DNS is a deployment. And again, we're just going to capture this in the same way, and then we're actually going to remove it. kubedns is a service, and again, let's actually capture this and remove it. And as we actually go through later, we're going to go through all of the details of these, so don't worry for now that we're actually removing them. If we then do a kubectl get all -a, the next 4 are static pods, and the clue is actually in the name there. Notice how they are named with the -node name. A normal pod's lifecycle is handled within Kubernetes. A static pod is controlled by a worker node through a YAML file that sits in a given directory. In this case, EDC Kubernetes Manifests. Remember, I mentioned earlier, if we take a look, we can see these 4 files. What we're actually going to do is move those files into our resources directory. And if we try a kubectl get nodes now, you can actually see that this errors as the worker has actually stopped these pods. The Cubelet was actually monitoring that directory, and as we removed the files, it's stopped the containers. if we check in nerdctl, those old ones are actually showing as created rather than up, i.e. they have transitioned to a stopped state. The final component remaining for us is the kubelet. So let's also stop this as well. So we'll just do a systemctl stop kubelet. At this point, I'm going to create two aliases just to actually stop and remove everything via nerdctl so that we actually have a clean base. And we're just going to run those. Okay, as you can actually see there, that's looking pretty clean. At the moment, we actually have our container runtime running. So systemctl status containerd, you can actually see that there. And we have a Cni configured to use the simple bridge and IPAM modules. Now, let's actually start enabling the Kubernetes architecture and see how we actually get on. The first component that we're actually going to look at is the Cubelet. The Cubelet is the primary node agent that actually runs on each node, and in Kubernetes, the Cubelet is often referred to as the worker. It ensures that containers are running in a pod, and as we actually have seen here, it runs both pods and static pods. So we're going to start the Cubelet just with systemctl there, and we can actually see that that's running. And if we take a look at the config, you'll notice the reference there to the static manifest. And at this point, from a nerdctl containerd perspective, nothing at all is running. Let's move the manifest that we actually created earlier for the Nginx pod into this directory. So I'm going to move that file, and we can actually now watch this with nerdctl. And there you go, you can actually see this, and you can see the pause container as well. And I'm just going to capture that ID, and we can actually inspect this like we would with Docker. So we'll do a nerdctl, we'll specify the namespace there, and we'll inspect that container. And right there we can actually see the IP address, and technically we can actually curl that IP address, and we see the Nginx welcome page. Let's actually see what happens if we now stop these containers. So I'm going to actually make use of that alias that I created, so nerdctl stop all, and we're going to watch what happens from the containerd with nerdctl viewpoint. And we can see that the old ones there transitioned to created, i.e. they were stopped, and the kubelet has actually recreated our containers accordingly. And we can repeat this a number of times, and we will actually see this as it actually happens. This gives you a real good understanding of the kubelet and a major function that it also performs as a bootstrap for actually starting Kubernetes. It's an inception point for the main components that Kubernetes needs to work as a whole. The kubelet starts, and in turn, it actually helps to start other components. So now our setup looks like the following. For now, let's just move that out of the way. And let's clean up. Okay, so next we're going to actually look at etcd. etcd is a consistent and highly available key value store used as the Kubernetes backend store for all cluster data. It's a leader-based distribution system, and when running in production, a 5-member cluster is recommended. So let's actually start etcd using a static pod. So we're just going to move that declaration there back into our manifests directory, and we're going to actually watch this with nerdctl. Okay, and with that running, we can actually try etcd out if we like. We'll install etcd-ctl, which is a convenient tool for interacting with etcd. And again, for anyone actually interested in doing the exams, this tool, etcd-ctl, often comes up as part of the examination question. So make sure that you actually learn this also. And now we can actually connect to our etcd instance. When kubeadm configured etcd, it would have done so with security, hence you see the various certificates here. We're going to use this as part of our etcd command, so we'll borrow the endpoints, the CA cert, the cert, the key, and we'll pass in the following to show us the endpoint status in a table format. And there you go, beautiful, we can actually see that. And we can modify this command to dump all of the keys that are being used by Kubernetes. If we actually just change that bit at the end there, so a get / prefix keys only, there we go, we've got all of the various different keys. Remember, this is simply a distributed key value store. So, for example, we can actually put a key. So I'll put a key of foo with the value of bar. And now we can actually retrieve that key, and you can actually see that there. With this running, we've added etcd to our overall picture. It's kind of in no person's land at the moment. Currently, we've been doing the bulk of our efforts directly with the kubelet. An important component of Kubernetes is the API server, and it is the main point of interaction for kubectl. When we exported the kubeconfig variable earlier, this pointed us at a file which tells kubectl how to actually talk to the API server, which leads us to another important component, the kube API server itself. The kube API server, it validates and configures data for API objects, including pods, services, replication controllers, and more. It services REST operations and acts as the front end to the cluster's shared state through which all components interact. So when kubeadm actually set up the cluster, the relationships between other components were configured. So if we actually trigger this as a static pod, so we're going to actually move this into place, and we'll just watch this start with nerdctl. And once again, we can now use kubectl like we did before. So now our setup looks like the following. At the moment, we're able to interact with Kubernetes, but what actually happens if we try to run something? Here we'll actually do a kubectl run of Nginx, we'll pass in the image of Nginx, and we'll actually watch this with kubectl get pods. Now, you could wait for an entire eternity here, and it's not going to change. It will be stuck, and the reason being, it's registered this request via the API into etcd, and now it's waiting to be scheduled to a node. Our configuration is very simple here, but what if we actually had multiple nodes, i.e. multiple kubelets running on different compute resources? This is the actual job of the kube scheduler. The kube scheduler is a control plane process that assigns pods to nodes, i.e. kubelets, and it determines which nodes are valid according to constraints and available resources. It ranks each valid node and binds the pod to the most suitable node. If we trigger the scheduler to run as a static pod, so we just actually move this into place, and again, we'll actually watch that. And you can see that that pod is now running. You can actually see there that that pod has now been scheduled. So now our overall picture looks like the following. Let's just clean this up. Okay, so we have some basic functionality, but what actually happens if we try to run something more complex, like a deployment? So here I'm actually doing a kubectl create deployment, Nginx, passing that image of Nginx. We specify the port as 80, and we're going to actually watch that deployment. Remember that a deployment doesn't just rely on scheduling a pod. It has replicas. So there's a controller aspect that needs to be running. And this is the role of the controller manager. The controller manager is a daemon that embeds the core control loops shipped with Kubernetes. A control loop is a non-terminating loop that regulates the state of the system. It monitors the state of the cluster through the Kube API server and makes changes accordingly to change the state to the desired state. We're going to start this again as a static pod, so we'll move that in and we'll watch the actual deployment. We'll do a kubectl describe deployment /nginx. So now, with that additional component, this looks like the following. So it's really coming together now. As we actually saw earlier, it would be nice to have a service for these just in case the likes of the pause container restart and our pods end up with different IP addresses. We'll expose this like we did before, so we'll do a kubectl expose deployment /nginx. We'll specify a type as cluster IP. We'll get the service and we'll actually try to curl that. Now, it's hanging, but all actually appears to be okay there from the output that you actually see there from the get service. And this is where the next component comes into play, the kube-proxy. Kube-proxy, the Kubernetes network proxy, provides simple TCP, UDP, and SCTP stream forwarding, round-robin, TCP, UDP, and STP forwarding across a set of backends. Let's reapply the kube-proxy declaration. Now, recall, originally, this was running within Kubernetes and wasn't a static pod. So we're using the YAML that we exported earlier and reapplying it so that it actually runs inside of Kubernetes. So we'll do a kubectl apply -f, so -f for a file. Now that we actually have that, we can access our service. So let's try that. And that's working as expected with curl. Lastly, let's check DNS using the convenient curl image. So we'll run this kubectl run --rm to clean up after ourselves, -i for interactive. We'll specify TTY. Curl is the name. We're going to use curl images and curl restart as never, and we're just going to execute the sh shell. And with that, we can actually now try curling that service. So curl nginx.default.service.cluster.local. And as we can actually see there, this isn't working. It's just pausing and hanging there, and that will actually time out. This, of course, is relating to our last two services, Core DNS and Cube DNS. So Core DNS is a Golang-based DNS server that stores DNS records and answers domain name queries. Cube DNS is the name of the service that serves on port 53, the standard port for DNS, so TCP and UDP, and this actually points at the core DNS pods. Now, historically, Cube DNS was a DNS server in Kubernetes in versions less or equal to 1.11. The service name of Cube-DNS was by design kept for compatibility purposes. So on really old versions of Kubernetes, you'll see that name structure, but it's actually different to what we actually have here. So if we actually reapply both of these, so we'll do a kubectl apply on the core DNS and Cube-DNS, and now we actually bring up our curl images container, and we actually try and curl that again, you'll see that that is actually working. And now our overall picture looks like the following. And we can see that this is now working as we would actually expect. So after following this video, you should now have a very good understanding of the functionality of the CRI, the Container Runtime Interface. In our case, this was Containerd. The CNI, the Container Network Interface, pause containers and why they are a super important component in Kubernetes, the Cubelet, etcd, the Kube API server, the Kube scheduler, the controller manager, the Kube proxy, Core DNS, and Cube DNS. Now, depending on the Kubernetes implementation, whether it's a production instance or a development instance like Minikube, whether it's running locally on your system or in the cloud, these components will be used in different ways and structured into logical groups accordingly. And sometimes this is where it can get confusing, but if you actually understand what the core components do, then it's actually not so overwhelming. So as an example, here's a common architecture overview that you may actually see. In this case, the main components are treated as the control plane, with the workers respectively listed there as 1, 2, and 3. Now, you know these components and what they actually do, regardless of how they are actually distributed in an architecture diagram. Sometimes you'll see this simplified even further, where the components are split into master/worker nodes and they leave out the specifics of how many are actually running. Lastly, you've also got the managed service type distributions of Kubernetes, like for example Amazon EKS. Generally, this is hidden away from you. Your control nodes are an endpoint that you would actually access with your kubeconfig file or variable. Under the covers, they would be using the same components that we've mentioned. You just don't see them. The workers, respectively, will have Cubelet, runtime, and the likes of kubeproxy for IP routing. If this has helped, subscribe to my channel and follow me on Twitter. And most importantly, tell your friends, tell your colleagues to actually watch this course. To fully cement this in, study the video, and if you want to check your knowledge, I now provide you here an optional quiz where every question is based on the content that you've just watched. Give it a go and see how you get on, and if you need to, go back and watch the video again. Further to this, there's also challenges which will really take your understanding of Kubernetes to the next level. So, thanks again. Here we go, and cue the awesome challenges.